Hi guys, in this video we're going to talk about Chiral auxiliaries, and throughout this, when there's a star that donates chirality. So, as you can see, we add the auxiliary to an R group, that just binds to the R group straight away. But another R group, and because it's diastereoselective, the R prime binds to the original R group, and the original R group now becomes chiral with the chiral auxiliary. The diastereomers separate, removing the auxiliary, and obviously the auxiliary can be reused, and that forms the enantiomerically pure R prime and R star, which is obviously something we're looking for. So the auxiliary should be readily available and in both enantiomeric forms, so the R and S form. There should be high diastereo control, and it should be easy to move, install, and obviously able to be recyclable as a catalyst sort of thing. So here's an example. We've got the Evans auxiliary here. It's just a simple look at what it is. So we're doing asymmetric enolate chemistry. That's how you form the auxiliary. So this is the actual auxiliary here, and we can use it in alkylation as well. So once again, we start off here using the auxiliary, and we add butyl lithium to it, and first, which shall go onto here, and then that chlorine can attack as well. And then after that, we can use LDA. We have got a thermodynamic enolate formation. So what we got here, we've got the lithium in close proximity to this oxygen up here. What have we done? I don't actually know what we've done here. Okay, so we've added LDA straight off the bat, I think. And that's bound there. And we form a double bond. Double bond can attack a bromine atom, an alkene, a bromine, and that can just add straight on as usual. So on the product, it's a thermodynamic product. The kinetic product is at a lower temperature. Use kinetic deprotonation. There's our LDA attacking. So basically, yeah, the lithium's just come straight on from last time. In this case, and we formed a double bond there from the hydrogen. Effectively, we've done exactly the same thing, apart from the lithium's just gone straight away. As you can see there, we get the same thing pretty much, apart from we get an E enolate this time. In this case, we had a Z enolate for the thermodynamic, and we just do exactly the same thing with the bromine. So might as well draw this out while we're here. Li can come down again, and then it's exactly the same sort of situation happens. Go down, attack there, and then we can remove the bromine, and then that forms the product, as you can see there, which is different to the one we've got there. Not bad mechanism. Obviously it took me a little second to get my head around, but just think about LDA. We wrote it out earlier, that's what LDA is, so make sure we remember that. And it just basically just attacks the hydrogen in both cases. Next we've got the removal of the auxiliary. We do that by lithium aluminium hydride. Yeah, we get a couple of products there, that and that. This can be reused. The auxiliary can be reused here, because that's what we form. So obviously we break that bond there and form these two, or we could add the KOH instead, and that just does pretty much the same, apart from we get a slightly different isomer instead. So yeah, that's pretty much it for that. Look at the Elman chiral sulfonamide. Once again, there's two sort of reactions. Sorry, my bad. There's a couple of steps in this reaction. So this is one of our reagents there. Use the lone pair to attack. Once the tin's been coordinated to it, obviously we had the tin first, sort of coordinates to it, to the oxygen. The nitrogen can attack at the double bond of the oxygen, push the electrons onto there. And then we've got everything coordinated now. We've still got the lone pair on the nitrogen can basically shift the oxygen and remove the oxygen effectively. And the tin to give us this product here, which is obviously just the removal of that group there and forming a double bond pretty much just there. So that's that mechanism done as well. We've also got chiral amine synthesis, which is something we'll just include in here as well. Obviously using the alumine sulfonamide again, and this time we're using a Grignard. As we know, Grignards can sort of attack the nitrogen double bond groups, which it sort of does while it's partially binding, forming this chair-like transition state. Obviously that's something that's key to remember, so look out for a Grignard with a alumine sulfonamide. This is in conformational lock, which means we're stereoselective. These things pretty much equal exactly the same, so that's what we get once we've done this reaction. Add ourselves on the R group, just there, and that's pretty much everything that happens in that step. Like I said, that equals that. We can show it as that. So it's just like a rearrangement of what we see. We can use a strong acid, HCl, using the chloride minus, which obviously the hydrogen protonates the amine part, and then the chlorine can attack the sulfur to remove that group by obviously pushing its arrows back onto the positively charged now NH2, and then we get the product, the non-selective product there. I think that's everything for this. Yep, that's pretty much everything. So next time we're going to be looking at catalytic asymmetric synthesis, and then a couple of other things such as the Jacobson epoxidation and asymmetric hydrogenation, and also an amino acid synthesis, and then that's it. So thanks for watching, and I will see you on the next one.